Okay, so as you're kind of finishing that up, I'm going to kind of start talking through this inverse variation stuff here. Very, very, very similar to what we were doing on Friday with the direct variation stuff. It's just a different formula. Tinley, on your phone? Done. Um, very, very similar. So the only difference is, so on Friday when we did the direct variation stuff, as one thing got bigger, the other thing also got bigger, right? Inverse variation is the opposite of that, where when one thing gets bigger, the other one gets smaller. So if you want a little chart like we did on Friday to kind of represent that, say you got X and Y there. If we just go 1, 2, 3, 4, we would be starting, our Y's would be starting with big numbers and going to small numbers. Okay, so as our X's are going up, our Y's are actually getting smaller. Okay. To make that work into a formula, what it is it's kind of like a reciprocal. So reciprocal, remember, is like the flipped over version of a fraction. It's kind of like the reciprocal of the direct variation stuff, where it's the same exact formula. So like y is equal to your k, or your constant of variation. So that's still constant of variation if you want to write that. That's still on top, but now our x, or whatever the other variable is, that gets moved to the bottom, okay? And same as before, it could be just, an x there to the power of 1, or it could be to the power of 3, 4, whatever they tell us. So same as last week, these are our things on how we could read these out loud. So they could read this as like y varies inversely as x to the power of n, or they could also use inversely proportional in there as well. Those both mean just an equation like that. And then again, k is our constant of variation. Can't be 0, because if it was 0 on the top and we divided by any number, it's just going to, again, kick out a 0, so that's not very helpful for us. But the important thing here is our x is always in the denominator of these, which means the bottom of our fraction. And then our steps to solve are exactly the same as they were with the direct variation stuff. We plug in, find our k value. Once we find our k value, we take that, come up with an equation, and then do our solving for whatever they give us. Okay, so first example here, these should be in your packets. It says the number of units u in a length varies inversely with the length L of the unit. Write an equation that expresses this relationship. Okay, so we've got number of units u varies inversely. So when we do inversely, our constant of variation, that k, is still going to be on the top. But this time it's over, and then it says the length L, so that length L is just going to go on the bottom. So that's all you would have to do for this setup. If it varies inversely, k on top, whatever it's varying inversely by, just goes on the bottom.
Is k always on top?
K is always on the top. Yep. 100% all the time, always on the top. Okay. The next thing here, you don't have to write this. If you wanted to write anything down, you could write down law of the lever, and then you could write down that formula there. But basically what this is, so you guys know what seesaws are, right? Like teeter-totter type things. So they use this as an example of kind of inverse variation stuff. So you guys know how seesaws work, right? You got like a little thing in the middle there, you got a person here, and you got a person here. If they're the same weight, what happens? It balances out, right? What happens if they're not the same weight? Like this one's really small, but that one's really big. What's going to happen to our teeter-totter? It's going to drop down there, right? So the heavier person's going to fall down, and the lighter person's going to go up. How would we get this to balance out again? So say we had a real heavy person here and a real light person there. What would the heavy person have to do to make it balanced? They would have to move forward. Okay, so if you've ever done this, like you're a little kid or you're your age and you got a little kid or something on there and you want to make the teeter-totter fun for them so they can still kind of go up and down. If you move forward here to like somewhere in there, I know that's just a made-up distance, but that'll actually balance it out. Okay, so that would be inversely proportional, because as your weight increases, you would have to get closer to that fulcrum. Okay, and that's kind of what this says here. That's the distance. You got it varies inversely as the weight. Another thought on this would be like carrying like a shovel. So like say you're pushing snow or something like that, and you got to carry that snow. Say it's real wet, heavy snow, and you're usually carrying it kind of like this. What do you have to do when it's real heavy snow? If the snow kind of starts falling down this way, what do you do with your hands? change them, yes. Wouldn't I probably move this hand closer so I got more strength to kind of hold up the heavy end of the shovel? Yeah, probably, right? So that's another kind of example of that is it's all kind of like levers and fulcrums and that kind of thing. I'll show you another example too with the flashlight when we get to that one, but we'll do a teeter-totter or seesaw example next year. Okay, so we got two people on a seesaw or teeter-totter. We got Carrie and Madison trying to balance it. Carrie weighs 34 kilograms and is 1.8 meters from the pivot. Madison weighs 38 kilograms. How far away from the pivot, pivot's just that fulcrum or like kind of that middle point, should she sit to balance Carrie? Okay, so right now what we got our little teeter-totter here. We got Carrie here at 34, and we've got Madison here at 38. We know Carrie is 1.8 away, and we're trying to figure out how far Madison should be away to get that balanced. If this person's heavier, are they going to be further away from the middle than 1.8 or closer? They're going to be closer, right? Because we got to be closer. Okay, so it's helpful here because we know that we can use that inverse variation. So that formula from the previous page was distance was equal to our constant variation K over the weight. So what we can do here is we can take Carrie's information, so weighing 34 and 1.8 meters. We can put that in there as our two pieces of information that we know, and then we can figure out Madison's weight, or figure out Madison's distance based on her weight. So we'll take the two we know already. So Carrie is 34 kilograms. That's going to go in for our weight. Be on the bottom, and then our distance that they are away from the pivot or the middle is 1.8, and then same as we were doing before, we just have to solve that for K. Once we find the K, we can plug that back in. Okay, so how would we get rid of divide by 34? Multiply by 34. And those are gone, so we'll have K is equal to, and then I just do 1.8 times 34, and I get 61.2. And then same as with the direct variation, we just found our K, so now we can take that and plug that back up there up top. So our formula would be distance is equal to 61.2 over our weight. Now we can take Madison's information there, that 38 kilograms, and put that in there. Where's that 38 kilograms going to go? For the weight spot, right? So we're going to go our distance is equal to 61.2 over 38. And then we just divide that out. So 61.2 divided by 38. I get, oops, it doesn't come out nice. So we'll go approximately 1.61. We'll go there. And what would our label for that be? Meters, because that's what we were measuring in. Yep, so that would be our distance, which it makes sense that that's a smaller number because Madison weighed more than Carrie did. Okay? All right, one more here. So the intensity I of the light is inversely proportional to the square of the distance d from the light source. Suppose the intensity of light is 6 meters from a light source is 30 lumens. So lumens just tells you the intensity of it. Find the constant variation, which is our K, and then determine the intensity of the same light 9 meters from its source. Okay. So setup-wise here, we've got our I is inversely proportional. So again, inversely is where we got the fraction. K is always on top. And then it's inversely proportional to the square of our distance. So I would go distance squared, or d squared on the bottom. And then to show you a visual, I brought a flashlight here to show you kind of what they're talking about. What happens when our flashlight's super close to the wall? Is it bright or not bright? Super bright, right? As my distance gets further, what happens to how bright that light is? It gets dimmer, right? So as our distance increases, what happens to our brightness? It decreases or lowers, right? So that's how that inversely proportional works, because if I'm super close, yeah, it's super bright, but then as I go out for my distance, then that brightness goes away. Does that kind of make sense? Okay, so that's kind of our setup here. So then we'll take our information that we know. So information we know there, We know the intensity of light at 6 meters is 30 lumens, so those would go together. And then we're trying to find our constant of variation, and we've got our intensity of the same light, or we're trying to find our intensity of the same light at 9 meters. Okay, so same as before, we start with the two that we know, so the 6 and the 30. Where's the 6 going to go? For the distance, right? So we're going to go equals, trying to find that k, distance is 6, so 6 squared, and then that pairs with our 30 lumens, right? And that would be for our intensity. What would we start with here? Square that 6. We'd have our k, 6 squared would be 36. And then to get rid of divide by 36, times by 36. Probably a decent sized number here. So if I go 30 times 36, 1080. Okay, so that would be my constant of variation because they asked us to find that. And then what do I do with that k value? Plug her back in. Yep, so we'll put that back up into our original formula there. So I would equal, we're going to put that 1080 in there, and then our distance squared. And then now we're trying to find our intensity at 9 meters. So where's that 9 meters going to go? In the distance on the bottom, yep. So I would equal that 1080 over, this time it would be 9 squared for our distance. 9 squared, 81, right? So 1080 divided by 81. We get 13.3 repeating, which is the same as 13 1/3. So you could either leave it like that, or you could round it if you wanted to, but I would leave it as one of those things. Okay? And that number makes sense, right? Because if it's further away, it would make sense that that number is smaller and less bright. Okay? All right, so that's it. So you got page 83, 1 to 15 for your assignment there.